Hello everybody, welcome back to another video. Today we're going to be solving a really complex problem because we have a lot of i's involved. Okay, let's get right into it. So, the problem is I tetration infinity. If you're not familiar with tetration, all it is, it's just repeated exponentiation. So just like you have I to the fifth power is equal to I times I times I times I times I, like 5 times, which is how this number works. I tetration 5 would be I to the I to the I to the I to the I. Oh, wow. To the I, just like that. A total of 5 times. So that's how that number gets used. Now, when you have a fractional tetration like this, I tetration 1/2, this is a topic for another video. It's quite difficult to make sense of this because how do you even have I to the I 1/2 times? But yeah, so now you have an understanding of tetration. It's just repeated exponentiation. So, let's understand this problem real quick. We can say I tetration infinity is equal to I to the I to the I dot dot dot, a total of an infinite number of times. So this repeats, so on and so forth. So now we understand the problem. Let's actually solve it. I to the I to the I dot dot dot, infinite times. Let's say this tetration is equal to A. Or I'll actually use Z, which is more appropriate because it's complex. Now, if you watched my other video where I talked about x to the x to the x infinitely is equal to A, and we have to solve for A, well, you can notice how we can say this exponent right here is actually equal to this entire tetration. So, what I mean by that is this I to the I to the I in the exponent of this I goes on for an infinite number of times as well. And this is actually equivalent to Z, because Z is I to the I to the I an infinite number of times. So if you're still not catching that, I'll quickly put this in red. And then I'll rewrite it like this. I to the I to the I to the I dot dot dot. I'll put this, so this is actually true as well because it goes on an infinite number of times. And this is equal to Z. And now you can see we just plug in Z into that exponent right there. So now we have, oh, my arrows are not that clean. There we go. Okay, so that means I to the Z is equal to Z because we just plugged in Z for that infinite tetration, which is equivalent to what Z actually is by definition. So now that we have I to the Z is equal to Z, we have to solve for Z. And remember, we're not solving for I here. Many people, they take the ln and then they divide and they raise it to the e, whatever, they do exponentiate and they solve for I, but we're solving for Z. We know what I is. I is just the square root of -1. Okay. So now, still, the Z is in the exponent, so we have to reduce this somewhat down to a coefficient or whatever. So let's take ln on both sides. If we take ln just like this, we can bring this Z down as a coefficient, and this becomes Z times ln of I is equal to the ln of Z, just like that. We divide on both sides. We have ln of I is equal to Z to the -1 ln of Z. Now, on the left-hand side, we have the ln of I, and most people will just leave the ln of I just like that because they think it's the most simplified form, except it's not. I did a separate video on this. However, if you, I encourage you to go watch that, but for those who just want to see the solution, I'll just quickly explain this in a few seconds right here. ln of I is equal to ln of -1 to the 1/2 power, which is equal to 1/2 ln of -1, which is just basic algebra. Algebra 2. So once we have this, we just have to solve for ln of -1. If you know Euler's identity, e to the I pi is equal to -1. This is what I'm not going to be proving. I'm just hoping you know this. If you don't, then you can go watch my other video. I encourage you to do so. If Euler's identity, e to the I pi equals -1, take ln on both sides. Cancel because ln and e are their inverse functions. Then you get I pi on the left-hand side is equal to the natural log of -1. And since we said that ln of I is 1/2 times the natural log of -1, we can say that ln of I is equal to I pi over 2, just like that. So now that we know what ln of I is, and that's our left-hand side, we can rewrite this as saying I pi over 2 is equal to Z to the -1 ln of Z. Now, how can we algebraically solve for Z on the right-hand side like this? Is there any algebra we can use or some trick or some nice way we can solve for this using just whatever we know right now? It turns out there is not. We can't just divide or add or do anything really to solve for Z on this right-hand side. But if you have been watching my videos for some time, I encourage you to do so, you will know about one of my favorite functions called the Lambert W function. It's an amazing function. Many great YouTubers use it, and my boy Lambert is a goat. Okay, so the definition of the Lambert W function is as such. The Lambert W of x times e to the x, just like this, is equal to x. I really should do a separate video on this because this is such a magical and useful function throughout mathematics. But all it's saying is just x, your parameter. This isn't your entire parameter, sorry. X times e raised to the x power is equal to x. It just returns that. That's the nature of it. And there are many branches to the Lambert W function, just like it looks like this. It's not really a function. That's why there's multiple branches. Fails the vertical line test. But I could go on a whole rant about that. But to keep it concise, just so you know here, the Lambert W is defined as the Lambert W of x times e to the x returns x. Now, I saw someone comment in one of my old videos that, hey, did you just define a random function to solve the problem because you couldn't do it in another way? Well, it turns out this is an actual function. There's an entire Wikipedia article on this. People have actually used this. It's called the product log. You can use it on Wolfram Alpha. It'll actually compute it. So there are ways of actually finding this, and I just showed you the little graphical representation. While not so accurate, you can definitely find it online. So it's not like I just came up with this. This is a real function. So back to the video. We have, what color? Let's use orange. I pi over 2 is equal to, how can we get this z to the negative 1 times ln of z into this form of x times e to the x? Now let's see here. I'm going to write ln of z, which is that ln. This z to the negative 1, I can just write this as e to the ln of z to the negative 1. Because I just said e and ln are inverse functions, they cancel, so this is actually equivalent. This is just valid algebra. So if I move from here, let's see, I pi over 2 equals ln of z times e to the ln, and by the way, this negative 1 in the exponent, I can bring this down as a coefficient, e to the negative ln of z, just like that. So are we ready to apply the Lambert W function? Well, not so fast, because the Lambert W inputs is x times e to the x. If we said this was x, and this is x, is it x? No, it's negative x. So we have to multiply. We have to make sure the thing in the exponent of e and the thing right here are the same. So to do this, we can just multiply by negative 1 on both sides. Now we have negative I pi over 2 is equal to negative, I'll put this in red, negative ln of z times e to the negative ln of z, just like that. Now you can see here this term right here and this term right here are equivalent, so then we can apply the Lambert W function. So Lambert W, we get the Lambert W of negative I pi over 2 is equal to, remember, this is the form we just studied on the definition of the Lambert W. This returns negative ln of z, just like that. Now we have the Lambert W of negative I pi over 2 on this the negative Lambert W of negative I pi over 2 is equal to ln of z. Exponentiate, just like this. E and ln cancel. Now we have z, ladies and gentlemen, is equal to e to the negative Lambert W of negative I pi over 2. Very satisfying answer, very clean. You have an e involved, you have I, you have pi too, think about that. You have that random number which comes from a circle, 3.14159. You have I, you have negatives. It's a very cool answer to such an interesting problem. That's as simple as I tetration infinity. And if you're wondering what this comes out to be, z, it turns out I have it here saved. Let's see here. I have it here somewhere. Oh yeah, it's right here. It is 0.43828 plus 0.36059 I. So yeah, it goes on. There's an infinite number of numbers in this, but yeah. So yeah, I hope you enjoyed this video. You can plug this into Wolfram Alpha. You will indeed get this. That's the solution to I tetration infinity. Let me know if I made any issues or do you have any questions below. Yeah, if you have any more video ideas, please let me know. Yeah, I hope you guys enjoyed this video. Thank you for watching. See ya.